Let us take another important question for class 12th physics, that is explain diamagnetism on the basis of electron theory. Also explain para and ferromagnetism on the basis of electron theory. How these magnetisms vary with temperature. Firstly, we will see the case of paramagnetic materials. What are paramagnetic materials? The materials which are weakly magnetized in the direction of applied magnetic field when placed in external magnetic field are called paramagnetic materials. What are the examples? Sodium, magnesium, tungsten, aluminium, platinum, calcium, lithium and antimony. On the basis of electron theory, we can explain paramagnetism. We know that electrons in atoms perform two types of rotational motions. Number first, spin motion of the electron is about its own axis. Number second is orbital motion of the electron around the nucleus. The net magnetic dipole moment is the vector sum of these two magnetic moments due to spin motion and orbital motion. But at room temperature, all the dipoles are aligned along random directions. So at room temperature, in absence of external magnetic field, net magnetic dipole moment of the given material is 0. But when this material is placed in external magnetic field, then because of its presence, these magnetic dipoles, individual magnetic dipoles, align themselves slowly along the direction of applied external magnetic field and get magnetized. So paramagnetic materials are those materials which get weakly magnetized or which get aligned along the direction of applied external magnetic field. This gets magnetized, and when temperature is raised above a certain temperature, that is called Curie temperature, this paramagnetic material loses its property. Means these magnetic dipoles again get aligned along random directions and their magnetism is lost. So with rising temperature, these materials lose their magnetism. Number second category comes that of ferromagnetic materials. Ferromagnetic materials are those materials which are strongly magnetized along the direction of applied external field, magnetic field, when placed in external magnetic field. And what are the examples of ferromagnetic materials? These examples are iron, nickel, cobalt and steel. And this ferromagnetism of ferromagnetic materials can be explained, can be understood on the basis of electron theory, which is also called domain theory. What is domain? In ferromagnetic materials, the individual electrons in atoms are bound by coupling. And what is this coupling? This is also called exchange interaction. In a small region, the volume of that region will be 10 to the power minus 18 meter cube. Nearly 10 to the power electrons get aligned along the same direction. Their magnetic dipole moments are aligned along same direction, and the group of these many electrons which are having magnetic dipole moments along same direction are called, they form a, this group is called a domain. In a domain, all atoms have magnetic dipole moments along same direction, and these are coupled or these interact with a special way that is called exchange interaction or coupling. But in absence of external magnetic field, these domains are randomly aligned. The effect is that in absence of external magnetic field, the net magnetism or net magnetic dipole moment of the material is 0. When this ferromagnetic material is placed in external magnetic field, what happens? These domains which are having individual magnetic dipole moments get aligned along the direction of external applied magnetic field. As a result, all domains align themselves along the direction of external applied magnetic field and get strongly magnetized. So ferromagnetic materials are those materials which are strongly magnetized along the direction of applied external magnetic field. What happens when temperature is raised? The ferromagnetic material changes into paramagnetic material when the temperature of the material is raised above a certain limit, certain temperature, that is called Curie temperature. So temperature affects the property of this ferromagnetic material, means these lose their magnetism and become less magnetized and become paramagnetic materials. Now we will switch over to third category of the material, that is diamagnetic materials. What are diamagnetic materials? Firstly, we will try to understand it. Diamagnetic materials are those materials which are magnetized weakly when placed in external magnetic field, and these will be magnetized opposite to the direction of applied external magnetic field. What are the examples of these magnetic materials? Gold, silver, copper, zinc, lead, mercury, diamond, and simple example is water, alcohol, hydrogen, and nitrogen. On the basis of electron theory, let us understand diamagnetism. Electrons in diamagnetic materials exist only in pairs, are always in pairs, having orbital motions in opposite directions. We will take an example. When external is shown is acting on the plane of this paper and directed vertically inwards, and one electron is moving along anti-clockwise direction, and in other diagram electron is moving in clockwise direction. What happens? Electron gets centripetal force because of this nucleus, and electrostatic force of attraction acts between nucleus and this electron. This electrostatic force of attraction provides it centripetal force, and in addition to this centripetal force, when a charged particle moves in magnetic field, it experiences a force that is called magnetic Lorentz force. And what will be its direction? Let us see. In first case, in first diagram, we will apply Fleming's left hand rule. The direction of flow of current will be shown by this middle finger. Electron is moving towards anti-clockwise, so direction of flow of current will be towards a clockwise direction. So this will be direction of flow, and the magnetic field is vertically inwards. So like this we will show, and clearly it is it can be seen. This thumb will show the direction of force acting on it. So magnetic force is acting opposite to direction of centripetal force. So its velocity, which is v1, will be reduced, and whatever is its velocity, the reduced value will be v0 minus delta v, because of this opposing force acting on this electron due to magnetic field, and its magnetic dipole moment will also get reduced because its speed is reduced. And as we know, magnetic dipole moment m is equal to I into A. If this charge is moving with a smaller velocity, smaller speed, then current will be reduced, because current is rate of flow of charge. So if V is reduced, this I will reduce, therefore M will reduce. So the reduced magnetic dipole moment, let it be M minus delta M. In other case, let us see, this electron is moving along clockwise direction. The centripetal force is again acting towards the center of this atom. And what about this magnetic force? We will see the direction of flow of current is like this. This will be anti-clockwise, and magnetic field is again vertically inwards. So the force acting on this electron will be towards the centripetal force. So it will be increasing the velocity of this electron. So increased velocity V2 will be equal to V0 plus delta V. V0 is its velocity when no external magnetic field is there. It's their natural velocity is V0 at that instant, and delta V is increase in its velocity. So V2 is equal to V0 plus delta V. Because of its increased velocity, its current will increase, then magnetic dipole moment will increase. So increased magnetic dipole moment, let it be m plus delta m. What is the difference in magnetic dipole moments? We will calculate it by subtracting from m plus delta m this m minus delta m. We will get difference as twice delta m, that is m plus delta m minus m minus delta m is equal to m plus delta m minus m plus delta m. This m will cancel the m, twice delta m. So this is net magnetic dipole moment. And what will be the direction of this net magnetic dipole moment? Let us see. Its direction is, resultant direction is towards the direction of m plus delta m, because we are subtracting m minus delta m from m plus delta m and we are getting positive quantity. That means the resultant direction is that of m plus delta m. So we will see the direction of magnetic dipole moment in this second case. What is the direction of magnetic dipole moment? We have already studied the atom acts as a magnetic dipole. Its direction is from south pole to north pole. What will be south pole and which will be north pole? When direction of flow of current is anti-clockwise, that side of this atom acts as a north pole, and when direction of flow of current is along clockwise direction, that side of the atom acts as a south pole. Now it is electron and we are seeing the direction of current, so flow of positive charge will be the direction of flow of current. So opposite to the direction of flow of this electron, we will see the direction of flow of current. So current is flowing in this diagram. In this case, this is anti-clockwise, means this side of this orbit will act as a north pole and opposite side will act as a south pole. So direction of magnetic dipole moment is vertically upwards. This is vertically upwards, and we have applied external magnetic fields, that is vertically downwards. What we find, the magnetism developed in this diamagnetic material is opposite to the direction of applied external magnetic field. That's why when placed in external magnetic field, the diamagnetic materials get weakly magnetized along the direction opposite to the direction of applied external magnetic field. This is how we can explain the theory.